So hello everyone. I will start my presentation on software architecture reasons from multidimensional spaces exploration. So the way I will do the presentation is that the presentation has several parts. So I'm expecting a strong exchange between participants because it's a very high level presentation, I must say. And at the end of each part of the presentation, I would like to have a small Q&A session. So don't hesitate to ask questions throughout the talk. So this talk has been made in collaboration with several institutions because it originated from research on multidimensional spaces, and in particular on multidimensional arrays. So multidimensional arrays, we currently have a proposal in the C++ standard, which is called mdspan. And I did some work on that topic at the Observatory of Paris in collaboration with NCSA and University of Illinois. And the goal of my talk today will be to explore what can be said on software architecture from a very specific example, which is the multidimensional arrays thing. So multidimensional arrays are everywhere in current computing. They are in scientific computing to do, for example, numerical linear algebra. They are in, you can use them to do some adaptive mesh refinement simulation. For example, that's something physicists are well used to in cosmological simulation, in astrophysical simulation, but also in fluid simulation, etc., etc. And to be able to run this simulation, people are often using multidimensional arrays somewhere. Multidimensional arrays are also everywhere in data sets. People who are using Python are using them, and doing data science are using them all the time. And as well as people who are doing physics, and especially in differential geometry, when they are using tensors, but tensor not in the sense of machine learning, but in the sense of physics tensors. And the list can go on and on and on. The problem is that even though multidimensional arrays are everywhere in computer science and in scientific computing, they are not currently in C++20, and they haven't been for the last decades. And this is a big problem because what happens is that people end up developing their own implementation again and again without people having a standard way of doing it. So the concept of multidimensional arrays in C++20 is that you can do it in a C style. So it would consist just this plain old C, good old C array, a multidimensional array. The problem is that even though it's easy to declare, the problem is that the dimensions has to be known at compile time, or at least at construction. And the problem is that when you want to deal with some different indexing strategies, then you have to manipulate all the indexes. You have to write indexing functions by yourself, and it's very error prone. The C++ counterpart of this is to put three arrays inside of each other. Note that the external dimension here is the first one to be written with std array. And the problem is, again, it's very verbose, and to deal with indexing strategies, then it's very, very hard to do. And the last way of doing it, that some people are doing, is just to deal with dynamic size array, is to put vectors inside vectors inside vectors, which is a terrible idea. And people are doing that because there is still currently no standard multidimensional array in C++, but people are working on that. And the last way of doing it is to use, for people who are doing numerical mathematical manipulation, is to use the val array, which shouldn't be used because it's just a bad mistake of standardization. So I've seen code, so it's very rare, but I have seen code where people are actually doing that. And people are doing all these things because there is currently nothing in the standard to do these things. So one question that arises is that why there is still no multidimensional arrays in C++20, even if they are in need everywhere, and most high-level language have them. Like if you are talking of Python, for example, Python have multiple libraries dealing with multiple multidimensional arrays, and it's very practical to deal with. And in C++, we still have nothing. And the reason for that is that because we want them done right. And the whole talk will be on what doing something right means in this context. And at first sight, the difference between good code and bad code is just that good code is like bad code, except it's good. Because, and the reason why I say that is because defining what we all can recognize what good code is, it's just sometimes very hard to define. We just know that it's good code. We just don't necessarily know why it's good code. So what I will be talking about today is what does good code actually means and how to get multidimensional arrays right. Because as I said before, in C++, if we standardize something, we want the thing done right, except that doing multidimensional arrays right is a very complicated problem, as we will see. So the first, going from there, in trying to define what right means, we'll talk about genericity, performance, and expressivity. So, as I said before, we can easily recognize generally what is bad code and what is good code. And from the developer standpoint, we often have this feeling of, when we encounter something that is very bad, we can definitely tell that it will be a nightmare to manage. And sometimes, rarely I must say, but sometimes we encounter some piece of code and we are like, wow, this thing is crazy. And all starts with these feelings for people. And that's how we recognize what bad code and good code is. In terms of projects, why is this thing important? The reason why it's important is that with bad code, people will really quickly accumulate technical debt. And technical debt is, so with technical debt, everything starts fine, but when you are making mistakes, you start accumulating them more and more and more. And at some point in the future, you will start to have to pay the price of them. And when you start to pay the price of them, then it means that your productivity goes down and it's harder and harder and harder to manage the program you're working on and people are working on. For good code, on the contrary, there is good code generally come hand in hand with good software architecture. And what that means is that everything will fit together nicely. And what I will explain in this talk is how we can make that happen. And in particular, in the case of multidimensional arrays, what does it mean? So to start with some concrete example, there is currently a proposal in the C++ standard about a multidimensional span, which is I would say the first step towards multidimensional structure. So in C++20, there is a new structure which is called mdspan. And for years, several people have been working on a proposal to the C++ committee to extend span to the multidimensional space. To start with something simple, simplification made on span is that first, it's a non-owning data structure, which means that it simplifies a lot of things regarding to allocation and that kind of things. What that means is that the first step towards multidimensional array, for the first step of multidimensional data structures, not having to deal with the allocation strategy and all of that makes things way simpler, even though it's already highly complicated. The second thing is that it is being designed only to deal with contiguous memory storage. And that also simplifies a lot of things. So mdspan for multi-dimensional span relies on four main components. The first one is the element type, of course, like the one you have in vector and in all containers. It's just what the mdspan contains. Then you have an extent class, which describes the shape of the mdspan. And by that, I mean the rank of the mdspan and what are the different sizes along each axis of the multidimensional array. Then there is a layout policy to specify the mapping between the storage and the indices. And the last thing is an accessor policy to specify how elements are being accessed in memory and how contiguous elements are being accessed. So the current mdspan synopsis, as of the last revision of the P0009 proposal, is the following. So the first thing you have is the extent policy, which defines what are the different, what is the behavior of the different size policy along each dimension. Then there are the layout mapping policies with three that are defined in the standard with a layout left, a layout right, and a layout straight. And each of these have an internal mapping class that defines the mapping, again, between the indices and the storage in memory. Then after that, there is an accessor which defines how to access each individual element, which is just dependent on the element type. And as I said before, the basic mdspan relies on the element type, the extent, the layout policy, which is by default set to layout right, and the default accessor policy. With that comes also a subspan, a sub-mdspan, that allows to access a sub-extent of the whole structure. And then after that, there are some tags that are, as I said, supporting the mdspan thing. So on top of the main class, there is also a default accessor that allows people to specify the mapping between the memory and the indices. And then on top of that, there is the extents policy, which comprise a set of constructors and assignments, observers of the domain of multidimensional index space, and some comparison operators. On top of dynamic index and dynamic extent. So what extent is that it contains the set of sizes that is currently held by the multidimensional span. So as I said before, mdspan is designed as the product of an element type, an extent allied policy, and XSR policy. And the $1 million question is, with mdspan, where are we in between terrible and amazing in terms of software architecture? Is mdspan the right approach? And what is the right approach to multidimensional data structures? And answering this question is actually not as simple as it may seem. Some people may raise the question of why should we even care if it's good enough? The problem with good enough is that the standard is full of good enough things. For example, at some point in the past, vector bool and val array were considered as good enough. The problem is that in practice, it turned out to be very bad design decision. And because in practice, it led to very, very complicated code to manage with a lot of strange side effects. And if we are going to standardize multidimensional spaces, we want to avoid software architecture disasters. So to be able to avoid architecture disasters and to have some kind of a guide in terms of software architecture, there are several possibilities. Because something done right, the word right is not well defined. And if we want to know if we are doing things right, we need to explain what right means. So by doing some research on the multidimensional arrays, it turned out that in practice, a good approach to be able to rate how close are we to a good architecture is to decompose the problem in three different things in terms of genericity, performance, and expressivity. So in terms of an example, there are some programming languages that are far more suited for certain things than for others. For example, if we take the C programming language, it will be, the C will be mostly dedicated to writing performance code. It's very hard to attain genericity, and it's very hard to attain good expressivity with C. On the contrary, if we take, for example, regular expression, so regular expression are not well designed for generic programming or for performance, but you can write a lot, you can specify a lot of things in a very, once you know how to write regular expression, I would say in a very concise and clear way. Then there are some programming language that lies in between two of them. For example, Haskell is a good programming language for people who are looking for genericity and expressivity, but it hasn't been designed to care for performance. And regarding C++, I would say standard C++, the classical C++, focus mainly on performance and genericity. You can achieve expressivity, but as I will explain later, it takes some non-classical C++ to do it. So this is the general picture, and you can take whatever code, whatever programming language, and it can be characterized inside this figure. So you can have a code that will be mostly focused on performance, but with a little bit of genericity. We'll have some code that will lie in between performance and expressivity with no particular attention to genericity, etc. And the good thing about this way of looking at things is that then you have three different axes to judge how good is the software. And that can help tremendously in terms of software architecture. So starting with genericity, because if we want to be able to deal with multidimensional spaces in a good way, in the right way, that means aiming for having the three all together. So the first thing is, how do we handle the genericity of the code? So to handle genericity, so genericity, having generic code, is that having a single code that can handle a lot of different particular situations and a lot of different use case and a lot of different application, etc., with the same abstractions. And to design abstractions, there are two main ways of doing it. The first approach is the top-down approach. So you set your theoretical framework with your big picture in mind, the concept and the general view. You set that, and then you will implement more and more things to go from the big picture to the application details and to the specific use cases. On the other hand, there is the bottom-up approach, where you start from all the application use cases and everything you could find. And from there, you design the big picture, the concepts, and the abstraction. And it happens that in some cases, we are inclined to use the top-down approach for software architecture. But what happens when people are doing that is that we start with a set of preconceived concepts. And the problem is that we might miss some things. And so this approach is very well suited for software implementation. For example, when you have an API that is high level, and then from this API, you want to derive the implementation. Then you start from the big picture, you implement all the things, and then you end up with your implementation that fits the needs. However, for software architecture, if you want to be able to handle as many things as possible, you have to start from the application, the use case, and find as many counterexamples as possible to be able to derive the concepts from there, to be able, in order to not miss a few things. So, as I said, the bottom-up approach is more suited for software architecture. So the idea is to start by accumulating a lot of concrete examples. So by example, I mean the different, for example, in case of the multidimensional arrays, that will be a lot of different use cases of multidimensional arrays, and try to see what are the common parts to all of these different use cases. The reason why designing abstraction in a bottom-up approach is better than in a top-down approach is that, contrary to human language, programming language are very bad with fuzziness. They need rigorous definition. And with human language, it's the opposite. Like, we are perfectly fine defining the big picture and then defining a particular example of that big picture. Saying that this particular thing fits there in the big picture, and if it doesn't fit really exactly, it's fine. We are able to handle it. The problem is that if you are doing that with C++ concepts, then you quickly run into problems, because the fuzziness in the first definition you have will lead to some incompatibilities in the future. And the problem with fuzziness is that conceptual approximation get amplified through higher layers of abstraction. which mean that in the software stack, if you are designing something very close to low-level thing, when it gets propagated to the higher level, language, to higher level libraries, to higher level application, then the small approximation that have been made from the start are used in an exploding manner in higher and higher levels, which means that a very small difference gets amplified a lot. And from something that was almost right, we can go to something that is totally wrong with unexpected use case with users doing everything, doing things that were not thought by the software architect. You will always find developers that are doing weird things with your code. The problem is that if their code is reused, then it means that the small difference are amplified again and again and again. And the thing is that to avoid that, there are two ways of avoiding that. The first one is to take the bottom-up approach, or to stick with very specific mathematical definitions. So in order to be able to design the right abstraction, the way to do it is to start with all the use cases you can think about, because every single one of these use cases will put more and more constraints on your abstraction. For example, if one use case of multidimensional arrays is linear algebra and the other is adaptive mesh refinement for physics, trying to do both at the same time will put high constraints on what is doable in the code and what is not doable in the code, in the abstraction. So by doing that, by trying to think about everything that someone may want, then and especially looking for the weirdest application, the goal will be to find boundaries of this giant space, of this giant design space. And because we cannot do everything, then the software architecture strategy will be to remove constraints one by one, by starting by the use case that are the weirdest and that are the most constrained. And for example, let's say if you have a very weird use case that is used in, let's say, 1% of application, and this adds a lot of constraints on your and this adds a lot of constraint on the software architecture, then removing these constraints first is probably a good strategy. And by removing constraint after constraint after constraint, we can finally end up with something that is reasonable to handle. As I say here, software architecture is not about what we can have, it's about deciding what we cannot have. So there is a question in the chat about not supporting embedded software. I wouldn't agree with that. If it all depends whether taking care of embedded architecture add a lot of complexity for very few users. If it's the case, then maybe the standard it shouldn't be the role of the standard to go for that. But if it's not the case, and if the community of embedded programming is sufficient, then it's one of the many applications we should try to deal with. So in terms, if we try to explore all the things that could be dealt with about multidimensional spaces, there is, for example, the question of contiguous memory, whether the memory is owning or non-owning. What about space filling curves to handle spatial indexing strategies? What about adaptive mesh refinement, etc., etc., etc. And this is just an extract of what we could think of, but by thinking more and more and more about making all the promises we could think of, we can end up with something that is extremely large. And for each of the design decision we make, so the question then is which of these things the standard should be handling, and which of these things the standard shouldn't be handling. And for each design decision can be expressed in terms of a matrix that is the following. So on one side, you have what you have and what you don't have in the library you are writing. And the other side is what you can have and what you cannot have in the library you are designing. So regarding the particular library you are writing, you're writing things in that space. The current abstraction, the abstraction that you're writing are covering is what corresponds to what you have and also what you can have. But also every design decision come up with something that you don't have, but things that you can have at the same time. If I go back here, for example, the mdspan is compatible with, let's say, some parallelization strategies, even though there are no particular things that are implemented in the library to do that. The interface will be completely compatible with parallelization strategies. So what you don't have, but what you can have determines how extensible is the library. Then there is the last one, which is what you don't have currently and what you cannot have in the library you are designing. So every decision you are taking about the software architecture come up with limits, things that will not be compatible with the thing you want in the future, with the thing you may want to write. And this is the very important thing to keep in mind when people are designing software. So the bigger and clearer the design map you are starting with, in terms of the number of examples, in terms of the number of applications, the clearer the design matrix will be for each design decision. If you have 100 different applications you can think of, then it will be very easy to see what are the design needs of the software. However, on the contrary, if you are just following a top-down approach, then it might be very hard to see what are the design limits that are introduced with the way things are designed. So currently, mdspan, it's dealing with contiguous memory, non-owning memory, static and dynamic size. Oops, this shouldn't be in green. This should be in blue. And memory layouts. And the current design, in my opinion, iteration strategies have completely been left on the side. And I think this is a big design decision because all standard algorithms are written in terms of iterators. However, the current mdspan does not provide iterators and multidimensional iterators. And the reason this decision was made is because dealing with multidimensional iterators might be way more complicated in terms of software architecture than only dealing with the current mdspan. Now, in terms of performance, so now that we have seen genericity, what about performance? So when we deal with C++, what we want is to reach zero overhead abstraction. Like all the abstraction people will come up with shouldn't bring any overhead. So to be sure that no overhead is introduced, the strategy to deal with that is by first benchmarking code that is very, very close to the hardware and that is also almost pure C code, and benchmark them on several architectures to be sure that nothing is missed. No performance is missed, and to be able to provide some ground state to compare what the abstraction are coming with in terms of performance constraints. And the strong constraint in the case of C++ is that in most cases, all high-level code should reach the same level of performance as the low-level code. So the good thing is that in C++, even when the compiler is not doing all the job, there is a way to deal with that. And the way to deal with that is to use metaprogramming. And by writing meta library that are acting on user code and doing some code transformation. So this is what people are doing when they are providing heavily templated libraries, or people who are implementing domain-specific language and stuff like this. So templates will react on the user code and can perform transformation at compile time. And once these transformations are performed, then everything is passed to the compiler, which generates binaries. And the only thing, so because we have these strategies, then the only thing that remains is to ensure that once the code is compiled through this meta-programming approach, that the generated assembly instructions are very close to the one that were generated for the low-level implementation. And regarding to the last axis, which is expressivity, so the definition of expressivity is the following. So there is a practical definition, which is how easy is it to use the software? How clear is the software? How concise it is? How precise and how accurate are the abstractions? For example, in terms of expressivity, when you are talking to a physicist, what they would like to have is something that is as close as possible to what they are writing by hand. So how to ensure that, so as I said before, physicists would like to have something that is very close to what they would write on a piece of paper. And good software architecture should try to match what the users are expecting. Having a formal definition of what expressivity means is actually far more complicated. And one can be found on this publication on the expressive power of programming language by Fellesen, published in 1991, but it's far more complicated than the practical definition. So in terms of multidimensional arrays in an ideal, we can start with what we would like to have in an ideal world. And in an ideal world, we would like something that would allow us to easily define a type that would be a runtime sized matrix. And this could be a particular way of specifying it. So we would have this template class and the array that will be provided, where you will have this double element type. And then you would have some magical structure or magical helper where you could specify how many dimensions are dynamic and how many dimensions are static. And in that particular example, having two parentheses would mean having a dynamic 2D matrix. Then to be able to do some compile time optimization, it would be nice if we could define things in a symbolic way with different variables. So in that case, we would have A, X, Y, and Z, with X, Y, and Z being 2D matrix. Then we could load the matrices in other data type, in other data structures, and then implement a symbolic formula, which would be A times X, this X here, the transpose of Y, and times Z. And to be able to, so that specifying thing in this symbolic formula would allow to further optimize the code and to do hardcore optimization. And it would be nice if we could then have just an interface where you could specify, okay, then the first parameter is equal to 0.5, then the symbolic X would be equal to this matrix, the symbolic Y would be equal to this matrix, and the symbolic Z would be equal to this matrix. And this would replace all the numbers and compute the result. And the thing is that all these things, so having things done that way would be very expressive because it's I would say easy to understand. It's not very verbose. Everything is clear, and hardcore optimization can be done. And the thing is that this thing can actually be done in C++. So the first thing I had regarding to the magic structure for shape to handle shapes, this was presented before on this particular talk, but the shapes of multidimensional arrays. And regarding the symbolic calculus, it can actually be done in C++. So the way it works is that we will be using, we'll first declare a singleton class, which has a default lambda as a template parameter. Okay, so this is the value of the lambda type. This is not the type of the lambda. Then inside the singleton, we can get the type of the lambda. And then if we want to be able to check the current location in the code, we can use C++20 version of source location. And to be able to compare different singleton, we can use the pointer to this location so that each singleton class with a different lambda parameter will have a different pointer here. Then from this singleton, we can write a default ID for symbols. So everything that will have this default ID will be equal to the same type, which will be equal to the one that we have this particular lambda defined here. And then we can define a symbol structure where an ID will be equal to the singleton of a lambda, a defaulted lambda that is written here. And each symbol will have a unique ID. And the way it works, so if it works, so I hope you can see. I hope you can see the God bolt. So the way it works is the following. So as I said before, we have a singleton and we have a symbol thing. And then if we type symbol X and symbol Y, and if we look at the pointer in X in Y, even though they are declared in the same way, then if I compile the code, sorry for that. If I compile the code, then regarding to X and Y, they will have different pointers here. So this is not the same type. While for A and B that have been declared with this default ID, they correspond to the same type. So again, when I compare X and Y, when I compare the types and check if they are the same, then is_same returns 0, and when I do the same with A and B, they return the same type. And this is very practical to achieve symbolic computation. So if I go back to that, oops. So the thing to remember when we are dealing with expressivity is that instead of starting with an implementation and see how we could simplify this implementation, it's often better to start with what users should be able to write, and assume that almost everything is doable with the right amount of metaprogramming wizardry. And even the case where metaprogramming cannot help you, there will probably be something that is close to what you want to define. So regarding to expressivity, a top-down approach is often better than a bottom-up approach, because in a bottom-up approach, we would start from the implementation and trying to simplify it. The problem is that clarity and conciseness will be incrementally improved, and the syntax of the code will highly depend on implementation details. But if we do it the other way, starting by the high-level user side and using metaprogramming implementation, then we can create really beautiful, I would say, embedded domain-specific language that are that have clarity and conciseness by design, ease of use by design, and the C++ constraints, language constraints regarding to the actual implementation would come after what the user would want to type. And this is in particular the case of mdspan. There are different directions of improvements in that regard. So regarding to the question, there is a question that is the following. So the lambda is like a compile time hash, meaning it's just used to distinguish each symbol. Yes, that's the case. The problem, so it's a type that is generated, that is different for each symbol, because for each new symbol you introduce, you have a different default template parameter, and therefore you have a different, you end up with different symbol, even though you type the same thing. So the only problem now in C++20 is that we cannot, it's not possible to, I think it's not possible to hash types at compile time, but in the future, if it's done, it would be better to have just a hash, to store a hash of the lambda instead of the lambda itself. So once we have genericity, performance, and expressivity, the problem is how everything is combined. And the thing is that generally, one start from the particular area, for example, very high performing code. And then the goal will be to introduce more genericity, and then with the generic code to try to reach for expressivity. So it's a very back and forth process to be able to have something that is at the same time generic performance, that have at the same time genericity, performance, and expressivity. And the thing that we might think it's something simple and just a gradient descent would allow to converge to this thing, but in reality, this design space is often far more complicated than that, and there is a lot of back and forth thing to do. So finally, about what does right mean in the case of multidimensional arrays and in general when dealing with software architecture. Being right often means being simple and elegant. So the criterion of simplicity means that users should be able to write simple code. The problem is that achieving simplicity regarding to the implementation side is often extremely hard. And because you have to deal with all the aspects of the three things at the same time, and it's combinatorial by nature. So you have to deal with combinatorial explosion to be able to deal with all of that. And in terms of elegance, it means that users should be able to find that the code they are writing is clear and everything fits together in a perfect way. And in that regard, software architecture is far more about finding the right balance. And in that regard, it's far more like art than an art than a science. And the last thing I would say is that programming, once I said everything that I said, programming is about all the lines that could have been written but have not been. A lot of companies try to rate the productivity of people by the number of lines that are written, but I would say it's actually, regarding to software architecture, is actually we should aim for the exact opposite. Because lines that are not written do not have to be maintained, and therefore this is keeping technical debt under control. So every time something is written, there is the question to raise is what could have been written instead. So in summary, about mdspan, we are probably on the right track with the decomposition in terms of element type, extents, layout policy, and accessor policy. However, me and several people are concerned about the genericity and expressivity of mdspan, mainly because at some point we should have multidimensional iterators in C++, and currently there is no certitude that the current design is compatible with what will multidimensional iterators be. And leaving this problem for the future means that we risk to have an incompatibility in the multidimensional domain. And regarding to conciseness, as I showed before, there is a lot of tricks that can be used in C++20 to make the code far more elegant and far more concise. Currently, it's not obvious whether the current design will be compatible with this level of expressivity that can be done. So to wrap up, I have talked about the GPU principle, which is a good guiding framework to think about software design. So focusing on genericity, performance, and expressivity. When you are dealing with conceptual approximation, the problem is that they are amplified throughout the software stack. To deal with genericity, a bottom-up approach is generally the best approach. And to find good abstraction, in that regard, the question is about finding counterexamples to try to push the boundaries of the design space. And then once the boundaries has been pushed, it's about choosing constraints. to be able to decide what will be taken care of in a particular software, and using the design matrix to decide to weigh between design decisions. Regarding to performance, metaprogramming can be used to achieve zero overhead abstraction. For expressivity, a top-down approach is generally the best approach. And I will conclude on the fact that software architecture is more an art than a science, and we should focus on simplicity and elegance, even though achieving that is very complicated. And programming is more about the lines of code that are not written than the ones that are written. So I think that's it. I don't know if I should answer the remaining question now, or if I should answer them later or in a subgroup. So some questions were about. So someone said it's not programming in software engineering. Yeah, that's correct. And I think the thing about the lines of code is something that is well known and very popular. It's just that some people sometimes forget that, and I think it's something very important to achieve good software. And I think I will stop here. Thank you for everyone for this for your attention, and as I said, if you have follow-up questions, we'll see that in the separate room. Thank you.